Alright, so today we're going to be talking about Raoult's law, which I have written up for us right here. Raoult's law is a law that governs mixtures of different compounds, and I represents a specific component of the mixture. And then this equation takes on the assumption that the mixture is ideal. So this won't work if mixtures aren't ideal, but it will if they are. So what this equation basically says is that, so the mole fraction of component I in the liquid phase, so X's are liquids, Y's are going to be for vapor, so that times the pure component vapor pressure, so this is the pure component vapor pressure of component I, and that is going to be equal to the mole fraction of the component in the vapor phase times the total pressure of the system. And so another way to write this term out here, this is just going to be equal to the partial pressure of component I. Alright, so that's Raoult's law, and we can use it to derive four specific equations to find bubble points and dew points for whatever system we have. So first we're going to be looking at the bubble point. So let's first talk about what a bubble point is. So a bubble point is if you have a container and it's filled entirely with a liquid mixture. So it's filled entirely with liquid, there is no air or anything. And then either the temperature or the pressure will be held fixed and the other will be increased until you see the first bubble of vapor begin to form. So for the bubble pressure, that would be the temperature that is being held fixed, and then the pressure that is being changed until a bubble of vapor starts to form. So that's our bubble right there. So let's start off talking about the equation for bubble pressure. So, as I said, temperature, we're going to know, and then pressure, it's going to be a question mark. So, let's find the bubble pressure. So this will be the pressure that at a known temperature, that the mixture will start to form a bubble of the vapor phase. So first thing we can do is we can know that pressure is going to be equal to the pressure of component 1 plus the pressure of component 2, or the partial pressure. So the total pressure is going to be equal to the partial pressure of component 1 plus partial pressure of component 2, all the way until the partial pressure of component N. And then, well, we know how to find the partial pressures using Raoult's law. So that means that the pressure is going to be equal to the mole fraction of component 1 times the pure component vapor pressure for component 1 plus mole fraction of component 2 times the pure component vapor pressure of component 2 all the way up until the mole fraction of component N times the partial pressure vapor pressure, the pure component vapor pressure of component N. Just like that. And then we can write this as a summation. So we're going to have our pressure is going to be equal to the summation of xi, so mole fraction in the liquid phase times the pure component vapor pressure. And then this will go from component 1 all the way up until component N. So that's just however many components you have. And so this is the equation that we're going to use to find this bubble pressure. And you may ask, well, how does temperature factor into this? You know, I don't see temperature anywhere in this equation. But we know the temperature, so that has to be important. And I want to remind you of the Antoine equation. So I did a video on this a while ago, but so the Antoine equation can be used to find this pure component vapor pressure, and that depends on T. So this term right here is dependent on the temperature, which we know. If we don't know the temperature, then we can't find this value. Alright, so that's the bubble pressure. Pretty straightforward. And so the bubble temperature is going to be, so we've got the same system filled with liquid. We want to know when the first bubble is going to form, but this time our pressure is going to be known and the temperature is going to be what we're trying to find. So, alright, this one down here. So this is called the bubble temperature. Alright, so we can actually use sort of the same idea that we had up here, where we have that the pressure is going to be equal to the summation from 1 to n of the mole fractions in the liquid phase times the pure component vapor pressure, like that. So then, however, this time we know this pressure, but we do not know the temperature that was used to calculate this. And that temperature is going to be hard to, rearrange this equation and solve for. And so what is most commonly done is to use a root function, such as in Python, which I'll show you how to do in a few minutes, to solve this. And so to do that, we're just going to need to rearrange it a little bit, get both of these terms on the same side. And so we'll have that. So we'll subtract this one over here, and so we'll have that the total pressure minus the summation from 1 to n of mole fractions in the liquid phase times the pure component vapor pressure is equal to 0. And that we can use our root solver for to find the temperature that is used in there. Alright, so the next quantity that we're going to want to look for is going to be called the dew pressure and the dew temperature. So this will be a different scenario than this. So this time we're going to have a container, but it's going to be filled entirely with the vapor phase. So over here we had it filled with liquid and we were turning it into vapor. This turn we're going to start with all vapor and we're going to look for the first drop of liquid that forms. So this is the dew point, and again we're either going to know the pressure or the temperature. So we'll start with the dew pressure, where, like the bubble pressure, the pressure is going to be unknown, but the temperature will be known. Alright, so we call this one dew pressure. Alright, so we're going to want to keep a couple things in mind. We're going to use Raoult's law, and then we also want to remember that the sum of the mole fractions of every component is going to be equal to 1. So this is, a pretty simple concept, but it's important to remember for the dew pressure. So we can write that out. So we have the sum from component 1 to n of the mole fraction in the liquid phase is going to be equal to 1. And then we can rearrange Raoult's law to plug into here. So we'll have Raoult's law So we have Raoult's law divided across by the pure component vapor pressure. We'll have the mole fraction in the liquid phase. It's going to be equal to the mole fraction in the vapor phase times the total pressure over the pure component vapor pressure. Alright, so then we can take this and plug it on into there. And we'll have the summation from component 1 to component n of mole fraction in the vapor phase times the total pressure over the pure component vapor pressure is equal to 1. So this is the due pressure, so we're going to want to solve for pressure. And you'll notice that the total pressure is going to be the same in every single term that we have, so we can pull it outside of the summation. So we'll have the pressure times the summation from 1 to n of the mole fraction in the vapor phase of the pure component vapor pressure is equal to 1, and then divide across by the summation to get p by itself on one side. So we'll just have 1 over the summation from 1 to n of moles in the vapor phase of the pure component vapor pressure. And so this is going to be the equation we're going to use to find the due pressure. So again, we know temperature, so temperature will be used to plug in for the pure component vapor pressure. And then we can use that to solve for the pressure. Alright, so then finally, we're going to want to look at the due temperature. So I'll write it up here. Due temperature right. So similar to what we did for the bubble temperature, we can use sort of the same idea and set it equal, get the two things on one side, set it equal to 0, and we use a Raoult solver to solve for the temperature, since temperature is going to be hard to extract from here algebraically. So we'll rewrite this up here, which is pressure equal to 1 over summation from 1 to n of the component of the vapor phase, or mole fraction of the vapor phase, over the pure component vapor pressure. Alright, and then subtract this over to that side. So I'll have pressure minus 1 over the same summation and we'll set that equal to 0. And so then this is going to be the equation that we use to solve for the due temperature using a Raoult solver. So there are our 4 equations that we can derive. Oh, I forgot to box this one up. Alright, there we go. So there are our 4 equations that we can derive from Raoult's law, and we can use them to find the bubble point and the dew points for whatever mixture we have.